Topic 2.10, Gravitation.
So today we'll start our conversation about the concept of gravitational force. And of course we've already talked about gravitational force because we've used that force as the weight of an object. And the weight of an object always, in our cases, we've always dealt with objects very near to the surface of the Earth, and so that weight always pointed downward towards the center of the Earth. The difference with the topic now is that we want to be able to, for example, leave the Earth and look at gravity on a much larger scale. And that's why this gravitational topic is oftentimes called universal gravitation, because this is a property that all objects with mass throughout the universe experience. And Isaac Newton was the first person to recognize the concept of gravitational force and the idea that gravitational force that affects people on the surface of the Earth might be the same force that's affecting the objects that we see, like the planets, the sun, and the moon, and other objects in the sky. So Newton sort of theorized what was the source of that gravitational force. Now, we've never thought about that before. We simply took the weight to be mg, mass times gravity, and accepted that there is this force and that we can calculate this force by multiplying the acceleration of gravity by the mass of the object. And Newton believed that the gravitational force was a result of the mass that objects have. In other words, mass, any object with mass, will have this thing called gravitational force surrounding it, and ultimately we'll talk about a new way of thinking about it called gravitational field. So Newton believed that the mass would affect the gravitational force in two ways. First of all, he believed that the force was proportional to the product of the two masses of the object. So in other words, if we have only one single object, then there is no force to calculate. The force of gravity is a force that acts between two objects which have mass. For example, you and the Earth, or the Earth and a table, or any two objects that are bound to each other through their gravitational force. It's not simply the one object's mass that affects it, it's actually both objects' mass affect it. Proportional means not that it's equal to, because force and mass are not the same thing, but that they're related to each other. So for example, if I double mass 1 without changing mass 2, the force would double. If I double mass 2 without changing mass 1, the force doubles. If I double both of them, then the force goes up by 2 times. So this is a direct relationship. He also believed that the gravitational force was proportional to the inverse of the distance between the two objects. So r is the distance between the two objects. Now that sort of stands to reason that as you get farther away from the object, the gravitational force gets weaker. It doesn't have to be 1 over r squared. It might have been 1 over r. It could have been 1 over r cubed. There's a number of ways that the force could have gone down as we move farther away, but through careful observations, he determined that the force decreases as the inverse square. So now let's think about how this affects the force on an object. If I move to a distance that's twice as far away, then that distance would become, that 2 in front of the distance would become squared to mean that the force was now 1/4 of the original amount. If I move to a distance 3 times farther away, I find the force is 1/9, at 4 times the distance 1/16, 5 times 1/25, and so on. So you can see that the force decreases very rapidly. If I start at any point and move to a point 5 times farther away, let's move 5 times farther away, I would find that the force was only 4% of the original amount, or 1/25 of the original amount that it was when I started. So Isaac Newton realized that these two objects are what affect the value of the force of gravity, and there's nothing else. There are no other variables which affect the force of gravity. So he suggested that there is an equation that determines the force of gravity between two objects, which is the product of the masses, the two masses multiplied together, divided by the inverse of the distance between them. Now there's a little bit of a problem because force is not measured in kilograms. These are kilograms for both of these. That gives me kilograms squared on the top, and on the bottom I would be measuring in meters, so I end up with kilograms squared over meters squared. Now, a kilogram squared per meter squared is not force. That's not the right units for force. So Isaac Newton realized that there must be some constant, some number in here that would allow the units to work out correctly. And so he suggested that that be called capital G, the gravitational constant. Now, let's think for a minute, what would the units of the gravitational constant have to be? Well, the gravitational constant must have units of, so a couple things I need to cancel. I need to cancel the kilograms squared, and I need to cancel the meters squared. So, to cancel the meters squared, G, since G is up on the top, G would have to be meters squared. Now, to cancel the kilograms squared, I'd have to have kilograms on the bottom of this number. That means kilograms to the negative 2. So these meters cancel the meters on the bottom down here, and these 1 over kilograms squared cancel the kilograms squared on the top. But my goal is to produce units of newtons, because that's the right units for force. So the units for the gravitational constant must be newtons meters squared per kilogram squared. Now, those are the units for that number. The value of the number, Isaac Newton was never able to figure out in his lifetime. Unfortunately, the equipment that he had was not sophisticated enough to be able to actually measure this number. This number turns out to be quite small. It doesn't negate the fact that he worked out the relationships. Without knowing what the value of the constant is, he still was able to determine the relationship between force, the gravitational force between two masses, and the distance between them. It wouldn't be until later, around 70 years later, that somebody was able to actually measure the gravitational constant. His name was Cavendish, and he determined the value of the gravitational constant to be 6.667 times 10 to the minus 11. So let me put a box around the formula for gravitational force and a box around the value of the gravitational constant. So let's take a quick example. We'll use the example that they give us in the book and calculate the gravitational force between two objects. And we'll pick two large objects that are not in contact with each other. This is a really important concept. When we talk about gravitational force, this is the only force that we've talked about that is not a contact force. All other forces are as a result of contact. The normal force, frictional force, tension. These are all things that result from contact. Gravitational force is very different, because gravitational force is called force at a distance, meaning that the two objects do not need to be in contact with each other in order to feel this force. And that's a very unusual thing when you consider most of the forces that we deal with in our daily life. Gravitational force, the one that we recognize and we respond to, but it's the only one that has this weird thing where gravity, the gravity of the Earth, can reach out and touch you without having to be in contact with you. So the sun and the earth are not in contact with each other. So this example, I'm going to go ahead and just use the example. This is question 1 on page 137. And they ask us to find the force between the sun and the earth. So, the mass, they tell us, of the sun, the mass of the sun is approximately 1.99 times 10 to the 30 kilograms. The mass of the earth is approximately 5.98 times 10 to the 24th kilograms. And the distance, the average distance between the earth and the sun, is approximately 1.5 times 10, my mistake, times 10 to the 11th. Meters. Be careful when you are given distances between two objects, because they may give you the distance in kilometers and you may need to make a conversion. The correct units here are meters. We need the meters squared to cancel out from the gravitational constant. So if they do give you kilometers, it's a little unusual to get the distance between the Earth and the Sun. Typically what they would say is 150 million kilometers rather than 150 billion meters. So the calculation is pretty straightforward. F is equal to G m1 m2 over r squared. So this is 6.667 times 10 to the minus 11 times the mass of the Sun, 1.99 times 10 to the 30th kilograms, 5.98 times 10 to the 24 kilograms for the Earth. And here's where people very frequently make a mistake, so pay attention. They forget to square the number on the bottom. I frequently see people write it out correctly, completely correctly. They put the square in, but when they make the calculation, they don't plug it into the calculator. So make sure that you do plug it into the calculator. And it turns out that the force of gravity between the Earth and the Sun is approximately 3.5 times 10 to the 22nd newtons. That is a massive number. Remember that the average weight of a person would be typically, for a human adult, the weights are probably going to be between anywhere from 500 up to maybe around 800 or 900 newtons. So less than 1,000 newtons is pretty typical for the weight of a human being, and this is approximately 3.5 billion trillion newtons, the force between the Earth and the Sun. And of course they have very large masses, so it should kind of make sense that they have a fairly large force. Okay, so we have the straightforward question where you're simply asked the value of the force. I've already addressed the second question in the book, question 2, which is what happens as you increase the distance. So again, it's an inverse square relationship, whether you look at it in terms of proportionality or you look at it in terms of the equation. The relationship between the force and the distance is inverse square. Doubling the distance causes a 4-time decrease in the force, 3 times more distance, 9 times decrease in the value of the force. Okay, so let's take a little bit of a different view of this, because this formula for force, Fg m1 m2 over r squared, we actually already have a formula for the force of gravity between two objects. It's called mass times gravity. That is to say, not the same g here. This is the gravitational constant. This is the acceleration of gravity. But we already know that the force of gravity is equal to mass times gravity. But now we have a new way of expressing this, and that is g m1 m2 over r squared. Now in this case, if I suggest that m1, typically the larger mass would be the first mass. So if mass 1 is the Earth and mass 2 is me, then this formula would be m2g, because I would be looking at my gravitational force. That is to say that I'm calculating my weight by taking my mass, multiplying it by the acceleration of gravity. Or alternatively, if I knew the mass of the Earth, and I knew my mass and my distance from me to the center of the Earth, then I could also calculate the value of gravity in that way. Well, if you notice that the two masses cancel out, and I end up with an expression for the acceleration of gravity at the surface of a planet, because of course I would be standing at the surface. This distance is between the center of the Earth and my center, and so I find that g m1 over r squared allows me to calculate the acceleration of gravity. And so that would allow me then to calculate the force of gravity on any planet. And they give a nice diagram. So if this is the Earth, and of course my mass would be here on the surface, and how far is it from my center to the center of the Earth? Well, effectively the radius of the Earth is basically the distance between the center of the Earth and my center, because my mass is only very small in terms of its size. It's only maybe a meter or a meter and a half. So this allows us to use this radius of the Earth to basically calculate the value of gravity. So they give a nice example where they calculate the gravitational acceleration on a larger planet, and then they calculate the gravitational force. We could, for example, pick a planet that we're a little more familiar with. We don't have to pick any random planet. Let's pick the value of gravity on, let's say, Jupiter. So in the back of the book, in Appendix 3, there's astronomical data which would allow us to come up with the mass and also the radius of these planets, and then also it gives us the orbital radius, not for the sun, of course, but the orbital distance between each of these objects and the object that it orbits around. Be careful to notice that the moon doesn't orbit around the sun, the moon orbits around the Earth. But for the rest of the planets, Mercury, Venus, Mars, Jupiter, Saturn, and on out, these orbital radius distances are the distance between the Earth, or between that planet and the sun. And you can see we already used for our planet 1.5 times 10 to the 11th as the distance between the Earth and the sun. So here's the numbers we need for Jupiter. We need the mass and the radius of Jupiter. So the mass of Jupiter is approximately 1.9 times 10 to the 27th kilograms, and the radius of Jupiter is 6.91 times 10 to the 7th meters. So let's calculate the value of the acceleration of gravity on the planet Jupiter. This will be 6.667 times 10 to the minus 11 times the mass of Jupiter, 1.9 times 10 to the 27 kilograms, and then we'll divide that by the radius squared, 6.91 times 10 to the 7th squared. Okay, so 6.667 to the minus 11, don't forget to put the minus in, times 1.9 to the 27th equals, divided by 6.91 to the 7th squared, and we come up with a value for the gravitational acceleration on the surface of Jupiter of 26.5 meters per second squared. Remember, the Earth's about 10. So that means that the value of gravity on Jupiter is approximately 2.5 times, a little bit more than 2.5 times greater than the value of gravity here on the Earth. In fact, we could calculate that by simply taking the 26.5 and dividing it by the 9.8 that we find here at the surface, and we get 2.7, and the word we would use for that is G's. Jupiter has approximately 2.7 times stronger gravity at the surface than the Earth has. And we could use this same calculation, this same equation, to calculate the gravitational acceleration at the surface of any object. So you might take the table in the back in the book and use that to try and calculate the gravitational acceleration on the moon, for example, on Pluto, on Mercury, or even on the sun, for example. If we could stand on the surface of the sun, what would the value of gravity be there? This is a simple calculation that you can make now using that appendix in the back of the book.